Instant hot water from a heat pump and a solution that fits in this tiny cupboard. Everyone said it couldn't be done, but what if they're wrong? I'm attempting to make something smaller than a combination boiler, but provides instant hot water from a heat pump. And if I do, this could change the way we heat water forever. Thanks to Maximus Wong 3092, who asked, if you're so smart, why not make an air source heat pump combi? Challenge accepted. The world is desperately trying to move from gas boilers to heat pumps. The problem in the UK at least is that 80% of homes use combination boilers tucked away in tiny kitchen cupboards to heat their hot water. So I'm attempting to create something smaller than the smallest combi boiler that can be powered by a small domestic heat pump and provide enough hot water for showers and baths for these 80% of homes. And if we can achieve this, we will finally fully unlock heat pumps for the 80% of homes that currently can't have one. Now, I've actually built a space-saving hot water solution before. Mini stores are already being installed all over the country, however, still only fit in a kitchen base unit. Generally, if you're removing a combination boiler, you're more likely to only have a kitchen wall unit's worth of space, which is only half the size. So just make a smaller mini store, right? Unfortunately, I tried that and it doesn't work. The smaller we made these, the more they fell foul to what I call the hot water death spiral. This is essentially a vicious loop where under high flow rate conditions, the water doesn't quite heat enough, which causes more water to pull through the store, which causes the hot water to cool more. It's mainly due to needing a bigger heat exchanger, and unfortunately, the smaller the unit, the worse the effect. Translation: cold showers. In winter. In Yorkshire. So how can we possibly go even smaller than the mini store and not immediately run into this risk? To go smaller, we had to rethink the entire concept. So I went back to the drawing board to try and totally rethink how to approach this. Until I had a 3 AM idea. What if the heat exchanger wasn't just for transferring heat, but storing it? If we could achieve this, we could possibly make this the most compact solution possible. Meet the Nordic Tech BA115 plate heat exchanger. At 500mm high and 250mm depth, it holds 15 litres of hot water and 15 litres of heating water, and boasts 11.5 metres squared of heat exchanger surface area. That's over 4 times larger than even the largest mini store. It's massive for a plate heat exchanger, about 70 times larger than the ones you find in combi boilers, but tiny for a hot water store. This isn't just a heat exchanger, it's a heat battery. And if it works, it's the core of what we will call the nano store. And unlike a cylinder, would fit very snugly in a kitchen wall cabinet. We had a plan. However, thinking this through, I come across 2 problems that would immediately put an end to this pipe dream. 1, a huge risk of severely scalding people, as this will likely be stored at well over 60 degrees. And 2, as soon as the heat pump turns on and attempts to send heat to the plate heat exchanger, it will instantly cool it down by pumping cooler water from the pipework and heat pump into the plate and causing the hot water temperature to immediately plummet. Being scalded immediately followed by a cold shower didn't feel like we were providing the best user experience. But thankfully, there was a simple solution that we previously used for the mini store. Blending valves blend the cold water with the hot to maintain a steady 45 degrees C limit and allow us to store much higher temperature energy in this little box without hospitalizing people, which is important, which essentially means more densely packed power and a longer shower time. To prevent the other problem of the store being cooled while the heat pump is warmed up, a second blending valve on the heating side of the plate will only open when the heat pump flow temperature finally reaches 45 to 55 degrees Celsius. And this allows the primary pipework and the heat pump to preheat itself and charge up with energy before beginning to open up to charge the plate heat exchanger. This kind of acts like an additional 7 to 10 litres of stored heat to boost the plate while it's in use. So, cold water comes into the heat exchanger here, heats up and leaves hot here. At this point, it blends in with the cold to leave ready at shower temperature. On the other side of the heat exchanger, the heat from the heat pump arrives at this valve and then circulates back round until it gets hot enough. Once it reaches temperature, this valve opens and allows more heat into the plate heat exchanger. Now there's all the theory out the way. I just needed to find somewhere to build and test this thing. Some of you may recognise my friend Simon from Urban Plumbers. He was one of the first to do our training a few years back and only lives around the corner, so I popped round. Check out his YouTube channel if you haven't already. Now, I would suggest anyone installing a system like this should size their heat pump for hot water demand rather than heating, and use a 7 kilowatt heat pump minimum, even if your heating power requirement is lower than that. Any efficiency losses from oversizing will be absolutely minimal, as larger heat pumps are usually more efficient anyway. We're testing on a 5 kilowatt heat pump. However, since it's 18-19 degrees outside, the output of this 5 kilowatt unit is equivalent to what a 7 kilowatt unit would be on a cold winter's day anyway. As you can see, we fully insulated this in Armorflex to keep the heat in, installed the 2 blending valves to control the heat generation, and managed to easily fit this in a 300 by 400 millimeter cupboard, and even had room to spare. Only the smallest combi boilers on the market would just fit into this space, so objective number 1 was a success. We just needed to see if this was actually going to work. Now, the average shower is 8 minutes long. After this point, the store should rapidly recharge, ready for the next use. If we hit this time marker, we've done it. If we hit 8 minutes of hot water at full flow, we're onto something big. Comment below, how long do you think it will last? Comment before watching, please, you little buggers.
You can see the heat pump has stopped now.
Yeah, so it's up to temperature. We've turned on the shower. We want this to run, but importantly, we need to see the heat pump kick in before we get a drop in temperature. If it doesn't kick in before we get a drop in temperature in the shower, then it's not really a combi, it's just a really small store and probably won't be of any use to anyone. So, there we go.
We're gonna time it and run it with this water-saving shower head. I think we're gonna get about 7 liters a minute from this. Start the timer.
Timer started.
Let's see if we get any hot water. And we're also gonna check if that heat pump kicks in to help us when the sensor reads the drop on the plate. Oh, it's getting warm. I'm getting something. Oh,
It's taken 50 minutes, 50 seconds to come through anyway, so
yeah.
Really the timer starts now, because now you jump in, so we'll shave a minute off of the shower time.
43, 44, 45, that's getting a bit hotter than I wanted.
That's hotter than anyone would shower typically.
The heat pump hasn't kicked in. Oh, I think it might just kick in. Yeah, 2 minutes before heat pump kicks in to support it, yep.
I mean, is 45 degrees showering temperature?
Yeah, it's too hot. It's too hot for showering. It's actually, you can't put your finger.
You should be at 41 or something.
If we can get 7-8 minutes out of this, or 10 minutes out of this,
oh my God, well, if you've
that
done
would
that.
be amazing. So we know the heat pump kicks back in early enough.
That's the heat pump kicking at the end there.
I mean, if the temperature's not dropping at all, you might have a combi here.
It does look quite good, doesn't it?
Flow is steady at 58. We're getting 5 kilowatts input, so we should not be able to run it for indefinitely. It will drop eventually.
Yeah.
Because that would need what? 7-8 kilowatts to run at this flow point? It is better than Minister. It doesn't drop the temperature.
Yeah. And it's smaller.
And the flow temperature dropped 2 degrees now. So it's dropping, but it's dropping.
So it's dropping slow,
very
that's
slowly.
what we want, yeah.
Very slowly.
Even though it's dropping, it's ramping up in power output at the same time, so it's doing its best to stop its cooling rather than adding heat. 5, 4, 3, 2, 1. We have an air source heat pump combi, ladies and gentlemen. It's still going at 43 degrees Celsius.
We did it! We create a solution smaller than a combi boiler that works with a small heat pump and provides enough hot water for the average shower. This was amazing. I literally could not believe it. And 45 degrees is way hotter than a normal showering temperature of 40 degrees Celsius. Why isn't someone out there already doing something like this? Then something unexpected happened. It kept going. What the actual Before I knew it, we were at 12 minutes. This didn't just hit the minimum performance, this was way more than enough for a shower. This would mean the next shower or bath would be almost immediately ready. Then we hit 15 minutes.
This is actually mental.
Then 18 minutes.
I said 20 minutes. It's going to be 20 minutes before it gets to 38.
At 20 minutes and still at 41.5 degrees Celsius, we were no longer testing hot water, we were testing endurance. Plus, we'd outstayed our welcome in Simon's bathroom. So we called it a day for this test. We'd not only hit our goal, we'd absolutely smashed it. That's everything we set out to do, and it all came together in what we're now calling the Nano Store. Take that, Maximus Wong 3092. Looking at the data, we'd hit a SCOP of around 2.7, and that was around 18 degrees outside, so 3 times more efficient than a gas combi boiler, despite hitting around 60 to 75 degree flow temperatures. Simon's actually done a whole video on this, so go and check that out. After some further tests, here's what the rough performance figures look like so far. And here's some additional results with a 9.5 litre a minute high flow rate shower head. Also, results will vary. We've got some more playing around to do here with the balancing valve settings, and obviously different primary pipework sizes in different homes will give different results. Let me know in the comments if you guessed that it would have worked that well, because I honestly did not believe it. I'm now not too sure why you would ever install a cylinder with a gas boiler, as this solution will almost certainly meet the demand for multiple bathrooms and users for much longer run durations with the oversized boilers in the UK. So a few of you might be wondering if running the heat pump in this way may break it. Although it's true that sustaining high temperatures from the heat pump can cause oil thinning and breakdown, this spends nowhere near enough time to risk that, and is also prevented by the compressor discharge temperature limits, as well as other parameters. Now, this will almost certainly work in much larger properties than you would think, as people don't really start their showers at the same time, and it should in theory stop the water while they soap up. However, if you did want more power, there's lots of additions we can do with this to bulk up the output for larger properties, such as multiple units, perhaps one per bathroom under the bath. Bear in mind, this will need to comply with G3 regulations due to volume though. Another option would be to use point of use immersion heaters at each significant outlet, like showers, and put them on timers or flow switches. This would give much quicker delivery of hot water and would only top up the shortfall in power when needed and no more. Now, this whole system can be installed as we've shown you here, assembling these 3 components in the best way to fit on your specific site. However, there is another large opportunity here. We'd also like to make this into a small insulated pre-made box that can be installed quickly into the cupboard and should reduce the installation time of heat pumps. Even more so, we'd like to also make this box weatherproof, so it can go outside where the primary pipes enter the home. This way we'd end up with even more internal room available than we started, reduce the installation time even further, and importantly, further reduce disruption to the home. If you're a manufacturer of solutions like this, please get in touch in the comments. And as always, we're not looking to commercialize this for ourselves. We don't patent ideas. We just want to see it made so we can get on and decarbonize homes. This could change the game, and you just saw it here first. But have we missed any tricks? Please let us know in the comments. This is just the beginning for the Nano Store. If you want to be part of the future of hot water and heat pumps, hit like, hit subscribe, and I'll see you on the next one.